So I received an email requesting that I speak a little bit about the things that we found out about the environment in this region. And our project, which has that long, complicated name, South African Coast Paleoclimate, Paleoenvironment, Paleoecology, Paleoanthropology Project, is meant to show that we do more than just archaeology, more than just human origins. The record here throughout the South Coast is super rich in evidence not only for human origins but also for climate change and environmental change. And so we've built a project that brings in about 40 different scientists from around the world, here in South Africa, Australia, United States, UK, France, from many, many different countries, doing all kinds of different techniques to try to reconstruct climate change and environmental change. And a lot of the reason that they're brought here is because of the rich record in human origins, but also because the ecosystem here, which you are all probably super familiar with, Fynbos, Cape Flora region, is of world renown in its diversity. There are, relative to rainfall and temperature, so normally species diversity of plants goes up with rainfall and temperature, but the Cape Flora region is just blows apart the relationship. It has way, way more species than what the rainfall and temperature would predict. So it's super unique in that characteristic as well. So that draws a lot of interest from scientists worldwide who are interested in how species speciate and how you get diversity, and then of course how to sustain it in the face of things like climate change and population growth and so on. So this region, this little stretch of land from pretty much from Cape Town to PE, maybe 150 kilometers inland, is of world renown and great interest to scientists of all of the paleo sciences. And I'm going to talk about, at the very end of the talk, an initiative I'm involved here trying to build a program of paleo science at Nelson Mandela Metropolitan University. And we actually just launched it on Monday. So it was a big event and big triumph for us. So I'll talk a little bit about that as well. And if you noticed, I put my name kind of small and the SAC P4 team bigger, because everything that I'm going to talk about rests on the very broad shoulders of my colleagues and the great productivity that they've had in this project. So I'm speaking for many, many people. So what I thought I would do is start off with some background on the biological story, because I'm sure, you know, I'm a person who specializes in human origins. I'm sure you're interested in hearing the latest information that we have on human origins. And we know quite a bit about human origins from two main sources of information. Now, the first is the fossil record, and that used to be the only record we had on human origins, right? So the fossils that we find in the cave sites and out on the landscape and so on, that used to be our best record. But now we're learning an enormous amount about human origins from the genetic record. And it has revolutionized what we've known. And to give you an idea of how fast the techniques and evolutionary genetics are operating, 10 years ago, evolutionary geneticists thought that we'd never be able to get a genome from a fossil older than 15,000, 20,000 years ago. Just last year, the genome of a fossil in Spain from a site called Atapuerca was published, and that fossil is minimally 300,000 years old. So they were able to extract DNA and reconstruct the genome from that fossil. It's astonishing, right? And then you can take that genome and compare it directly to ours. Pretty amazing. And we expect it may even go back further. I don't know if you saw in the science media just a couple weeks ago, they were able to isolate blood vessels in a dinosaur fossil. Right? I don't know which dinosaur it was, but you know, the dinosaurs go extinct 65 million years ago. So that's astonishing technologically. So I'm going to summarize all that information for you in this one slide, called the biological story. And at the bottom, I've put the global record for climate change. This is a temperature change record. So it's from the Antarctic ice cores, and we reconstruct the temperature from the delta deuterium record in the ice core. And the Antarctic ice cores go back to about 800,000 years ago, so that scale is in thousands of years. And when that little line is up here, we're in a warm phase, and when the line is down here, we're in a cold phase. So that's a glacial phase versus an interglacial phase. And of course, today, we're in an interglacial called the Holocene, and it's lasted for about 12,000 years. And we would expect the Holocene to last about 40,000 years, based on the rise and fall of temperature change in the record. And those geological epochs, those are driven by orbital changes, changes in the tilt of the Earth and in the shape of its orbit around the sun, which changes the amount of radiation that hits the planet. But a take-home message that you can see here is that the vast majority of the last 800,000 years, the Earth has been in a cold phase. So it's been in a glacial phase, which means that the landscape, the land and the sea, looked very different than it does today during most of the last 800,000 years. And I'm going to talk about that. How can we learn about that? Okay, so we know from the fossil record and the genetic record that the Earth was inhabited 700,000 years ago by two main lineages. And what I mean by lineages is these are groups of species that share ancestry. Okay? So they share a common ancestor probably around 800,000 years ago. And then around 700,000, they begin to split into two main lineages. And I'll just call them the Eurasian archaic lineage and the African archaic lineage. And we know from the fossil record and from the genetic record that up until about 400,000 years ago, there was quite a bit of gene flow. So there were hominins moving in and out of Africa so that genes were connecting those two populations. But then, right around 400,000 years ago, that gene flow stops. And when you have gene flow between populations stop, they begin to speciate. Okay, so they begin to move in different directions evolutionarily. And we don't know exactly why that happened, but I think it probably had something to do with the formation of the Sahara Desert. And the Sahara Desert cut the populations in sub-Saharan Africa off from their movement in and out of Africa. So very little gene flow. And then there was some budding off of new lineages or species. You can think of them as interchangeable. This one, the Denisovan lineage, we just learned about a few years ago, first from its DNA. So they had a finger bone, a pinky, from a cave called Denisova in the Altai Mountains in Russia. And they thought it was a Neanderthal pinky bone, and when they sequenced the DNA, its genome was beautifully preserved in the fossil, it turned out to be a totally new species of human that we had never seen before. So pretty stunning result. And each of these lines, if it ends in a circle, that means that species ends in extinction. Okay, so that it's obviously not with us today. And then I know all of you have heard of Neanderthals before. You may have referred to somebody as a Neanderthal, which kind of means you have an idea of how they behaved. We actually don't, the scientists. And they end in extinction, and they also bud off of that lineage. And, so the picture I want you to keep in your mind is that, 200,000 years ago, the world has at least 4 lineages. 1, 2, 3, 4. We have one lineage today. It's the modern human lineage, or one species. And that's actually quite rare in the history of the planet. Normally there has been many species of humans, and now we have just one. And around 200,000 years ago, the modern human lineage appears here in Africa. So we have the first Homo sapiens fossils in Africa at this time, and we can see from the genetic record really, really clearly that lineage appears in Africa. And that lineage leads to everybody alive on the planet today. Okay, so we're all descended from that lineage. And then around, and this date, we're actually getting it very, very close to figuring out exactly when it happened. A founder population leaves Africa, and it's sometime between 70 and 54,000 years ago. We're really, if I was here 6 months ago, I would have said 70 and 40. But I can say 70 and 55 because there was a new modern human fossil found in Israel, and some stalagmite had dripped on its head after it died in the cave, and they dated the stalagmites. A very precise dating technique, 54,000. And that's likely a member of the founder population. So that guy, he died before 54,000 years ago, okay, because the stalagmite dripping on his head obviously postdates his death, right? So he could have died, unless it, you know, dripped there and he stood there for okay, so that population that leaves Africa, we know was actually quite small, a couple hundred people. And all Eurasians are descended from that founder population. So that creates those two main lineages on the planet today, Eurasians and Africans. But something interesting happens, and it happened very, very near the Out of Africa event. Though some of those Eurasians interbred with Neanderthals, such that they picked up pieces of their DNA, so that all Eurasians have snippets of Neanderthal DNA in their genome. And it varies between about, and it's different for every single person, it varies between about 2 to 6%. It just depends, right? And we actually, there was a modern human fossil dated with radiocarbon to about 42,000 in Siberia just recently, and he had a beautifully preserved genome. And what's really interesting is he has really large intact segments of Neanderthal DNA in his genome. And the fact that they're intact, you know, your DNA sorts every time it's passed on. The fact that they're intact means that the interbreeding event was just several generations before he existed, right? So that was a pretty amazing find. And then, you know, this Eurasian population then gives rise to all the amazing diversity of ethno-linguistic lineage and groups all over the planet, right? Like at Contact, 1778 in Australia, there were 450 ethno-linguistic groups, 450 languages. You know, Papua New Guinea, amazing language diversity. So modern humans had this enormous capacity to radiate around the planet, but also had this proclivity to break up into little groups and separate themselves by evolving languages that the group next door couldn't understand. So that's kind of an interesting aspect. And but what's also interesting here is the group that made it to Southeast Asia and then eventually built seaworthy vessels and sailed to Australia. And you can't see Australia, right, from Southeast Asia. Those people had to be capable of envisioning a land that they couldn't see, one that they trusted in their courage to make it there and conquer for their families. This is incredible to think about. They made it to Australia sometime around 50,000 years ago. But that population interbred with Denisovans. So that the Melanesian group, which includes Australian Aborigines, have little snippets of Denisovan DNA in them. So what we now know, right, is that all these other these three lineages go extinct, but many of us have little pieces of them still left with us as a kind of a calling card, I guess. And then what's kind of interesting finally is that there was a very ancient African archaic lineage that was still present here in Africa, and it interbred with some Africans just after the founder population left Africa. And we know after because Eurasians don't have any snippets of this DNA, and Africans don't have any Neanderthal or Denisovan DNA. You see what I'm saying? That's how we can see the difference in the splitting of it. So, right, and that brings us up to the present. So just to give you an idea, and now I'm going to talk a little bit about how climate and environment plays into this. During interglacials, Africa tends to be warm, like the rest of the world, but also much wetter. So we know, so here's a reconstruction of Africa during an interglacial that existed between 230,000 and 195,000 years ago. The Sahara Desert was a grassland at that time, and it was actually quite well watered. So we have many of the lakes and the rivers have been mapped, and there are hippo fossils and crocodile fossils. Quite a rich environment. My point being is that people could cross back and forth. And during these interglacial events, there's a lot of, the red arrows represent gene flow. There's no boundaries between populations, so there's probably quite a bit of gene flow taking place, and that keeps it one species, right? But then 195,000 years ago, and here's we're zooming in on our climate record again. Here's, 200,000. So I'll just round it off. From 200,000 years ago to about 130,000 years ago, we enter this really long, cold glacial that we call marine isotope stage 6. So that interglacial map I showed you was back here. Now we're entering this long, cold glacial phase. And if you remember, the modern human lineage appears during that glacial. Okay, so now kind of bringing the climate and the human evolution together. And here's a reconstruction of what Africa would have looked like during a really hard glacial phase. So the Sahara is twice as big as it is today. So most of Africa is actually desert during these glacial phases. Namibia and Botswana, the Kalahari and the Namib Desert have expanded quite a bit. We know the Central African rainforest, which is represented in green, was for the most part gone. What I've hypothesized in a couple of papers, and maybe you've read the Scientific American paper, which was a public science version of the scientific articles I've written, is that Africa probably had about 6 different places that could harbor populations, what we would think of as a refuge. And one of these gives rise to all modern humans on the planet today. So that origin lineage, right, which I told you, the modern human origin lineage, appears in one of these places. Now, I've argued it was the Southern African subregion where this origin lineage appeared. I have colleagues working in North Africa who would have argued that North Africa was a candidate region. But actually, I think we can now strike it off because they've done quite a bit of research, and they don't have any occupation in North Africa during marine isotope stage 6. So if you don't have it during stage 6, the origin lineage can't be from that area. Okay, and this is why we're really hammering away at trying to find sites that sit between 200 and 130,000 years ago. We also have some very strong genetic data that would suggest that the origin lineage comes from the Southern African subregion. And here's just a couple of papers that published very, very recently. Hunter-gatherer genomic diversity suggests a Southern African origin for modern humans, both in very, very prominent journals. So there's quite a bit of genetic data pointing to Southern Africa as a key place. Okay? Now, I based my argument on something slightly different. And this is the cover of the Scientific American issue that I published, the public science version, and the kind of detailed scientific version of the argument is published in the Journal of Human Evolution. And my argument for pointing to the Cape Floral region was what I can call an ecological potential argument as a refuge during global cold phases. So basically what I'm saying is that if we're looking for a refuge zone, you have to argue, why would hunter-gatherers persist there? What's the logic? What's the reason they would be in that area during a glacial phase and not in some other area? So I'll just briefly explain why, and I know that some of you are familiar with this. Here's the world's 6 floral kingdoms, and as many of you know, the Cape is its own floral kingdom. And that's because it's super unique relative to any other vegetation system anywhere in the world. Cape Flora region. It's recently been slightly enlarged and is now called the Greater Cape Floristic Region. And that was in a book, the argument behind that's in a book that was just published in Oxford University Press. And my research group wrote the paper on the human occupation of this area. And obviously one of the key biomes in the Cape Floristic region is the fynbos. And of course Mossel Bay is really strategically positioned to look at human occupation in this area because we're right at the east-west centroid of the Cape Floristic region, the fynbos biome. But there's some things that are even more important, which I'll point to in a minute. Okay, so one part of the argument was that the Cape Floristic region has a really high abundance of plants that are edible by people. And the plants I pointed to in particular were plants with underground storage organs, what we call geophytes. So geophyte plants are an adaptation to dry climates, mostly winter rainfall climates. So in this classic paper in 2006, Prosh et al. Looked at the diversity of geophytes for Mediterranean ecosystems, and Mediterranean ecosystems are the ones that receive winter rainfall. And you can see that the other Mediterranean ecosystems fall pretty nicely on that line, which is the number of species by area. And we know that in ecology there's a functional relationship between the size of an area and the species. But look at the Cape. It's way off the charts. It has way, way more geophytic species than any of these other environments. And many of those are edible. Many of them are poisonous. And one of the things we're doing right now, we have a study going on in Stilby where we're going out with local people, we employ local people, and we do these collection experiments where they go out and forage for for bulbs. We measure the return rates, and then we test them for their nutrition. So we're trying to kind of rebuild the knowledge of the edibility of those species. The other thing that's absolutely crucial here is you have a confluence of two very, very rich oceanic currents. The Benguela upwelling, which spins in this direction, but creates a rather arid and harsh environment on the west coast. And then, of course, the warm tropical Agulhas current, which comes down here and retroflects back to the east. But one of the things that we learned about the Agulhas current, so your summer rain comes from the Agulhas current. And if the Agulhas current wasn't flowing, you wouldn't get that bimodal or all-year rainfall system that you have here. We now have a series of cores offshore that show that the Agulhas current has been flowing unimpeded for the last 800,000 years. So we know that the Agulhas current has been steady, and in fact it's increased in its power during glacial phases. And the Agulhas current keeps this area much warmer than what it should be. So it's a warming aspect. And the reason that's important, of course, is as the world swings into a glacial phase, since the Agulhas current continues, it keeps the temperature here moderate, where other areas would get colder and harsher, but also your summer rain would continue. So you would continue to get rainfall throughout what's normally an arid phase in Africa. And of course, the clash of those circulation systems creates a super rich oceanic environment. And you have off the coast here one of the richest marine environments in the world, and the intertidal zones here are more productive than probably any place else on the planet. So what I argued was it was the shellfish providing the protein and the Cape Flora region providing the carbohydrates, both of which would be protected during glacial phases by the specialness of the environment here and would still be productive. So the argument was an ecological possibility argument. We have all these great resources. We know from their specialness that during glacial phases they would still be productive and people could forage them. So then we had to go out and do the archaeological research to see if that was supported. Okay? Okay. Yeah, both are resilient in response to colder temperatures. But here's the other leg to the argument, and this is kind of new. I'm going to talk about some new research that we've been doing. As you know, the Cape Floral region doesn't have a lot of large game. It's mostly small buck, right? Grise buck, bush buck. And even though when the early travelers came through here, that every once in a while they'd occasionally see a hartebeest or something like that, it's not like East Africa. You don't have these gigantic migration ecosystems or even the bushveld, right? It's not like that. And the reason is because the vegetation is dominated by shrubby plants, there's not a lot of grass, and the grasses that are here are not particularly palatable because of the rainfall system. But when we look in the archaeological sites from the Pleistocene, we see these guys. Lots of wildebeest, lots of zebra, lots of hartebeest, and we see an entire suite of large ungulates that are extinct today. So for example, there was a buffalo called the extinct giant buffalo, Pelerovis antiquus. Its body size was 4 times the size of a Cape buffalo, and its span of its horns were from here all the way over to here. Okay, and wide like this. So obviously it wasn't running around the forest. If you see what I'm saying, right?
Yeah.
So we've always had this paleontological problem. Where do these animals live? They cannot live on feignbass vegetation. So I'm going to explain to you, we figured it out, and we have a whole series of papers that are coming out, being published right now, that I think provides a very compelling explanation for how these animals end up in this environment in the Cape Floral region. Okay. So just to work our way toward that, here's the main sites on modern human origins in South Africa, and I've put on this axis the age, okay, down to 180,000. So Klassies River, amazing site on the Tsitsikamma, Bloembaas, not far from Stilbaai, Diepkloof over on the west coast, Boomplaas in the Swartberg, right, great site, and Sibutu in KwaZulu-Natal. These are the main sites. Here's Pinnacle, the record we've developed at Pinnacle Point over the last 15 years of research. So a couple of things to draw your attention to. One is we've developed the longest record here. It's a composite record. We've built it by working at a series of sites, and we started at 13B. We did some work at Cave 9, and we've been working at PP56, a rock shelter called PP56 since 2007. And we're still digging there. And you might think, why is it taking so long? Well, when I started there, I thought I had 2 meters of archaeological sediment. We now have 14 vertical meters. Imagine 14 vertical meters of human occupation from bottom to top. It's like, I'm never going to get out of that cave. Every time we do a little, we come over to, we find new layers, and it's an amazing site. It's well worth committing that kind of time to. And so we've developed a record that's continuous from 130,000 to 50,000, and then we have an occupation down here, smack in the middle of marine isotope stage 6. That's when the origin population occurs. And that right there is why, the first reason why Pinnacle Point is so famous. There's only 3 sites in Africa that have dates at that origin point. And Cave 13B has 3 occupations that date to that period. So we know people were here, and they were producing a pretty spectacular archaeological record. So let me just say a few things. I'm sure many of you have been to PP13B before. There's a picture of our excavations. We've developed some super state-of-the-art excavation technique, so our project is famous alone for that. We don't even use tape measures. Everything is measured with lasers directly to computers. So we can measure at less than millimetric accuracy, where you can't even get close to that with tape measures. And if you were to come out to site, you don't even see paper on site. Everything goes directly into computers, tablet computers. It's a pretty sophisticated system. And here's PP56. It's, like I said, it's actually not a cave, it's a rock shelter. And the sediments are built up under that shelter. And they once would have, you know, here's your talus deposit, they once would have gone way, way out like that, but they've been cut back by the Holocene high sea stand, which has ate away at the deposits, and now the only ones that are left are tucked under this rock shelter. There's another picture, PP13B over here, PP56, and there's a number of other sites that look extremely productive in the Pinnacle Point area. So our first major result was published in Nature in 2007, and that paper was, had a huge impact because it documented the first time that we have any evidence for people using sea coastal resources back to 162,000 years ago. So that's that isotope stage 6 occupation. They were going for rocky intertidal zone shellfish, and we even find whale barnacles. And these are the barnacles that adhere to the skins of whales. And obviously they're not hunting whales, but they're almost certainly scavenging wash-up, stranded whales that wash up. This is also the earliest evidence we have anywhere in the world for intentionally modified pigments. So people were taking ochre and grinding it into powders, which they could have been using for cave paintings. We don't have cave paintings that old, but they could have been using it for that, or painting their bodies. And we know also that some of the ochre was intentionally heated to increase its redness. So a lot of ochres naturally occur yellow, and that's the iron mineral goethite, and if you heat it at up to maybe 300 degrees centigrade, it'll transform to hematite and turns a bright red. And we know people were doing that. In 2009, we published the next major result that showed an invention of a very early pyrotechnology. So sorry. Let's see if it picks it up. I shouldn't have moved it. Go there again. Let's see if I can get that back up. There we go. Okay. Right. So what they were doing is they were taking silkrete, which is a naturally occurring rock in the Cape, and in its raw form you can't really make stone tools from it. And under very special conditions they were heating it up to around 300 to 350 degrees centigrade. And once you heated it, it does kind of a light vitrification to the rock, and then they were making stone tools out of it. So that beautiful bifacial spear point that you see there was experimentally made from that piece of silkrete after it was heat treated. And prior to this, the earliest evidence we had for heat treatment anywhere in the world was 20,000 years ago. So people all the way back at 162,000 had understood how you could take a stone and change its engineering properties under controlled heating conditions to improve it so you could make a stone tool out of it. And that's what we mean by pyrotechnology, right? And all of our technology is based on, for the most part, using heat to transform things, steel and platinum and so on. This is the beginnings of it. Okay, so, but here's something else that's kind of interesting. So, how do you heat treat stone, and what is the process for making a stone tool out of it? Well, normally when you make stone tools, you just need to get the stone. But to heat treat, you have to procure wood, right? And as you know, normally you go to a braai, not many people are using fynbos wood, right? It's all the Australian alien stuff where it's shipped down from Namibia. That's because you don't have a lot of trees here in the fynbos. You have a super high diversity of shrubs, but it's not great for a braai. So this is actually a thing we're trying to solve, because the heat treatment comes and goes over time. Sometimes they really do it a lot, other times they don't do it at all. And we think it has to do with the availability of wood. I think we're going to figure this out. So how do you do it? You procure your stone, you procure your wood, and you build a simple kiln. And you can't just throw it in the fire because it cracks. We have found, and actually we have ethnographic accounts, mostly from Australia, that people would build a sand bath. They put the stone in the sand bath, and they carefully put the charcoal over the top. So the fire's already been built, and you're pushing charcoal on top, slowly raising the temperature. If you raise the temperature too fast, it cracks, right? Kind of like pottery. They'd slowly raise it to 350 degrees centigrade. You hold it there for a few hours. And then you take it out, and now you can flake it. And when you flake it, you can produce these amazingly sophisticated stone tools. And I'll show you what some of these look like in a little bit. Okay. Now, the next big major result that we published, and you'll notice I keep pointing to this journal, Nature and Science. Nature and Science are the two most prestigious scientific journals in the world. All scientists want to get in them. They're very hard to get a paper in. And we've had great success. In 2012, we published this paper in Nature, and they liked it so much they actually put an image on the front cover that was developed by my colleague Eric Fisher, who's amazing. And if you know Pinnacle Point, you actually know this spot. It's high up as you're climbing down to PP56, and he created this image of a Khoisan man and put it into the thing. I thought it was really powerful, and they obviously liked it too. And what we published on was the earliest evidence for what we call microlithic technology. And microlithic technology is the production of small tools. So that's a scale, 1 centimeter, and they're just these little tiny pieces that we call microliths. And you might wonder, well, why are they so important? Okay. They're important because what you do is you take a piece of stone, and you have to set up the stone perfect. So you flake it really, really carefully to create a special flat platform. So you can knock off these long, thin flakes that we call blades. Okay? So you can see the negative scars, and you carefully knock these off. And then you take those little blades, and you notch them so that you can snap them very controlled. So you actually end up breaking them. And then you blunt them on one end, and leave them sharp on the other. And they create these little triangles and crescents. And you've probably seen these in the museums. But here's the thing, they're too small to be held in your hand to be useful. Too small. And a lot of them are way smaller than that. So what did they do with them? They're mounted in composite tools, normally weapons. So what you see here, these are from archaeological sites. So these are not from South Africa, but from various places in the world. Each of these is made out of bone. And this is an experimental one made out of bone. And they're normally mounted, so you take a bone, and these are darts. And you put a groove into it, and then you glue the little barbs into it. And the whole point of this is to create a very small, light, deadly weapon that you hurl with a leverage-assisted technology. And what I mean by leverage-assisted would be a bow and arrow or a spear thrower, an atlatl. We call it an atlatl in the United States. And atlatls are amazing. Guys who know how to use atlatls, the Australian Aborigines were the experts. They never had bows and arrows. They always used experts. They could hit a bug on a tree at 60 meters with an atlatl. Okay? So these are atlatl bolts. Now, when you find microliths, it's almost always associated with leverage-assisted projectiles, what we call true projectile technology, either atlatl or bow and arrow. So the implication of our paper, and the reason it was so important, is we showed that at 71,000 years ago, people here had sophisticated projectile technology, way earlier than any place else in the world. So now you're seeing the pattern, right? Early ochre, early shellfish collection, early heat treatment, early projectile technology. We just have an enormous amount of evidence for very special behaviors taking place early here first.
And here's some Australian Aborigines. Photograph taken in 1914 with atlatls. So there's the atlatl, right? And what that gives you, it gives you an enormous advantage over a hand-cast spear. A lot of distance, a lot of power, and a lot of accuracy. Okay. So let's come back to the climate, and I'm going to wrap my talk up with some discussions of how we know how we can reconstruct the climate. Let's come back to these glacial phases. And I'm going to talk specifically about this glacial phase right here. So those early atlatl technologies date to around 71,000 years ago. And you can see we've got this long glacial, then we go really warm, and then the planet declines into a glacial phase, and then jumps back up into the interglacial that we're in today. But I'm going to talk about this one specifically, right here. What was the Cape like during that glacial phase? And we've done a lot of work on that, focusing on it because we want to know why they switched to technologies like atlatls at that point. Okay, now to do that, what we argue is you need to build a whole new model of what the environment looked like. And we call it a paleoscape model. So this is a scientific model, right? And when we say model, models can take place, can be all kinds of things. It can be a model that sits on a table, which is a simplification of reality. It can be a mathematical model. It can be a computer model. It can be a model that you walk into when you walk into a museum, and they create a hologram, and you see what the environment looked like. And wouldn't it be great if we could take the paleoscape model that we develop and have people experience it at the center that will be built here, highlighting the work that's being done. Okay, so it's a dynamic model. It's not static. It's something that we can run and changes over time. And we use it to create formal hypotheses, quantifiable hypotheses about what people did in the past. Instead of just kind of making it up in our minds, we can generate predictions of how humans would have behaved from a model like this, computer modeling. But it requires a new approach, and that's an approach that our scientific team is leading. And we're working with a big group of people to try to create this paleoscape model. And it'll happen through what we call an integrated paleoscience. Okay. So let me just show a couple steps. How do we do it? I'm going to, because it's actually gotten very complicated, but I'm going to show you, just illustrate it with two pieces of the model. One piece was published in 2010 and led by Eric Fisher. And that model creates estimates of the distance to the coast. If glaciers are advancing and retreating, we know sea level rose and fell. So for example, 18,000 years ago, sea level was 120 meters lower than it is today. What did the land look like? We need to know that. Eric built us a model for looking at it. Okay, see if I can get it to run. Okay, so here's your current coastline, right? And off that coast, you have this long, broad platform called the Agulhas Bank. And it's very, very gradually descending. And we've done a high-resolution geophysics study off this coastline, and that was led by Dr. Haley Cawthron, who's a South African scientist at the Council for Geoscience. She did her PhD on this work. But it should run if I tap it. So, there we go. Okay. Okay. So this is a three-dimensional reconstruction of the coast and the offshore platform. And I'm just going to show you, it's going to zoom back in, and you'll see how gradually it descends. Okay? See how gradual. And then it drops. Okay? My point being is that during these glacial advances and retreats, the coastline moved back and forth very, very rapidly. Now, how rapidly? Well, here's a reconstruction of the output of the model. Here we are today. during a full interglacial, and the coastline is right here. And here's how much land was exposed during a full glacial. So Mossel Bay and Pinnacle Point is here. That's 100 kilometers of space. And what we've been able to show is that a landmass as large as Ireland was gained during glacial phases and lost during interglacials. It's actually half of your land area in the Cape Floral region, expanding and contracting. Okay, and here's the output of the model. Here we are at distance in kilometers from Pinnacle Point, and this is the time scale. And each one of these dots is the output of the distance to the coast. So I'm just going to bring your attention to one set of data. That's 137,000 years ago. The coastline, 137,000 years ago, was 95 kilometers away. At 125,000 years ago, it was where it is today. So over just a few thousand years, it went from 95 kilometers away to right up against the cliffs where it is today. That's why we need these models. So we can see how the landscape changed and develop hypotheses of how people would have responded. Okay, so that's one part of the model. Now let's look at vegetation. Okay, another part of the model. We have to model the vegetation to see how it changed. And that was led by Miriam Bar-Matthews, who was a scientist I recruited from Israel. She's one of the world's best at using stalagmites to reconstruct climate change. And we published this paper in 2010. So how does it work? Well, here's the base of a stalagmite. And stalagmites grow by water dripping, and they grow up in these laminations, right? So here's one we cut. Each one of these big drills that you see here, we can date that with a technique called uranium thorium, and these are the ages, 84.2, so that's 84,000 years ago, 81,000, 80,000. And each one of these little drills is for looking at carbon and oxygen isotopes for us to reconstruct the climate. So how do we do that? Well, you have a big vegetation change that occurs across this east-west axis. And I'm going to simplify it down to the basics. Over here you get really, really strong winter rain. And over here you get strong summer rain. And those rainfall systems have different isotopic signatures. And we can measure them from the stalagmite. And we can tell whether the water was coming from the east or the rain was coming from the east or the west, or was coming in the summer or the winter. And you have grasses that use a photosynthetic pathway that's called C3 over here and C4 over here. And C4 grasses are tropical grasses. They have to have summer rain. C3 grasses are winter rainfall grasses. So classic fynbos vegetation. And we can see in the stalagmite whether the grasses that were growing above the cave followed the C3 or C4 photosynthetic pathway. Okay. I'm not going to get into all the chemistry about it, but it's well known, it works great, and we've been applying the technique here. So just to give you an idea, here's some oxygen isotope measurements on the rainfall. It's depleted, and these are the measurements of the oxygen in the rain, and it's enriched. So your summer rain is enriched in oxygen 18 and depleted in winter. And we've measured it here at Mossel Bay. If you go down to Monroe House where we work out of, you'll see we're always capturing the rain, and then we measure it in mass spectrometers. And what we can show here is here's the months of the winter months, and you can see the rain is depleted, has a negative measurement. As you go into the summer rains, it gets enriched. So we use that to interpret what seasons the rain was falling in the past on stalagmites. Okay, so let me just show you what it looks like. Here's a record that we developed and published from stalagmites at Crevice Cave at Pinnacle Point. The scale is 90,000 years ago, so there's 90, and that stalagmite runs to 53. Okay, so here's the carbon signature, here's the oxygen signature. The line in the middle is the mean, the running mean. And these are records of global temperature change. And you can see the stalagmite follows those pretty nicely, right? So the climate environment here is reflecting globally driven climate change. So basically what we see is that from 90,000 years ago to about 74,000 years ago, you have quite a bit of winter rain and C3 grasses and kind of a western flora. So a very Fehn-Bosse winter rainfall system. Then as we move into the glacial, 74,000 years ago, summer rain becomes more important and you get C4 grasses. So the eastern vegetation is sweeping in to this region as you get more summer rain, as we would predict. And then as we move out of the glacial, you move into more winter rain and C3 grasses. So that glacial phase that I told you we're interested in, it has more summer rain than what you have today, and it has a more eastern flora. But also think, right, the coast is retreated because it's a glacial. I'm just going to show you this very briefly. Mira and her PhD student Kirsten Braun, who did her PhD extending Mira's work. Here's Mira's record. Kirsten has pushed it all the way back to 450,000 years ago. And we're just about to publish that. That is the longest, highest resolution climate record that we have from a land-based record anywhere in the southern hemisphere, developed here at Pinnacle Point. Super important record. Okay, so here's our phase 1 model. Okay, a simple model. When climates are warm, here at Mossel Bay, the coast is nearby, you get more winter rain, so you get kind of a winter-summer, all-year rain system. You have lots of C3 grasses, and you have a more western kind of flora. When we move into colder phases, glacial phases, the coast retreats enormously, and we have this big plain out here. You get more summer rain, and you get more C4 grasses moving into this area. And something to remember, those C4 grasses are more palatable to animals, right? It's always the summer rain grazing areas that are rich for cattle and so on. Okay. So this helps us solve a paleontological problem. Remember the paleontological problem, right? Now we know why we have animals like that during glacials. The coastline retreated. It created this big flat plain off the coast of Mossel Bay. Summer rains came in from the east, increasing the palatability of the felt. Gave these animals a place to live. So this is what we think it looked like. Okay, again, getting to the model. During a glacial phase, we have the coastline opens up and it's flat because it's been planed off by millions of years of water rising and falling. Flat, where you have this rugged environment here. This is not the right environment for a migration ecosystem. This is what migratory animals like. Nice and flat to move across. You have summer rain in the east, winter rain in the west, and during glacials that summer rain increases. But here's the thing that's important. To generate a migration ecosystem, you have to have a push me, pull you. The animals have to be drawn to something, they have to be pushed out as well. That's how you set up a classic African migration ecosystem. And this is perfect for it. Animals would migrate to the east in the summer, and they would migrate to the west in the winter to take advantage of the green graze. So we think it would look something like this. They start in the east, they move west in the winter, and then they move back. And these little bullseyes, they represent the daily foraging radius of a hunter-gatherer. They're about 20 kilometers. So our hunter-gatherers, we think, have developed those projectile weapons, and they appear during that glacial phase because they are now adding big game hunting to the roster of foods that they take from the Fehn-Bosse area. So what's happened is we see the evolution of a special environment for our unique species. So originally I hypothesized shellfish plus tubers made this place special. Now the chair has 3 legs. Big game hunting during these glacial phases. There's no environment anywhere in the world that looked like this, right? You know, you can go to coastal California and they have a rich marine ecosystem and they have a rich plant food collectible ecosystem. They do not have a big game migratory ecosystem of tens of thousands of animals moving back and forth that people. This was a uniquely rich place for hunter-gatherers to survive glacial phases. So our team is building the paleoscape of this special environment. And we hope to be able to show you more and more of that as the years go by. And who are we? We're the South African CSIR. We're doing climate modeling. So the climate model that predicts your weather, we've collaborated with the South African scientists there, and we've taken that model and we've moved it to an American supercomputer. So that model requires supercomputers to run. Climate models are very complex fluid dynamic models. And we're loading it with glacial conditions and using it to predict what climate would have been like at glacial phases. It's a very unique study. We're working with botanists and climate modelers and vegetation modelers at Nelson Mandela Metropolitan University in PE. And we're also working with scientists at Stellenbosch University. And they're doing a lot of the foraging studies on the plants and animals, and a lot of the modeling work is based here and at the CSIR. I'm from Arizona State University. We're doing vegetation modeling. We're doing also foraging studies, and of course we do a lot of the archaeology and paleontology. The Exceed Supercomputer Center in the United States has been very, very generous to us. I mean, it's hard to communicate this, but running a supercomputer costs millions of dollars a week, right? And they've devoted significant computational power to this study. So they're contributing the high-performance computing facilities for the climate model. So let me just wrap this up with some conclusions. We know some things very clearly. All modern humans are descended from this progenitor lineage that appears sometime between 200 and 130,000 years ago. That lineage lived in Africa and then spread out to the rest of the world. The genetic record suggests that that lineage lived in the southern African subregion, right? It's a hypothesis. It's not proven. I want to emphasize that. It's a hypothesis. It has strength from a variety of sources, but it's still a hypothesis. The South African coast has all the features that conjoin to make it an excellent refuge during the cold phase, when modern humans evolved. And it seems increasingly plausible that this region is the birthplace of modern human lineage. We still need to subject this to strong, tough scrutiny. Science works best when you're not trying to prove your hypothesis. Rather, you're trying to falsify it, right? So we have a lot of students and a lot of PhDs, and we work hard to challenge our own ideas. And that's crucial. That's why I'm emphasizing that it's a hypothesis. The next phase of our research, we need to approach the problem with this new multidisciplinary paleoscience approach that unites natural and social sciences. And it's important to remember that your country is the custodian of that data set that generates it. And naturally, then, you have to take the lead in building these new science teams. That makes the most sense. So to that end, I'm helping Nelson Mandela Metropolitan University establish a new center for African paleoscience. And the ribbon cutting was on Monday, so I went there, I gave a talk. They've devoted the funds to hire 2 scientists, brand new center that will have a totally multidisciplinary structure to it. And that is going to be the base for an entirely new team of scientists that we will build over the next however many years it takes. But I have to say I'm really impressed by the support that the administration of NMU has put into this, and the Vice Chancellor there has personally put together the funding to stimulate this and make it happen. So I'm proud to be a part of that group. Thank you. So I'm happy to take some questions if you, yeah.
Can you use some of the gas field drilling results to help you with your hypotheses?
For the climate work. It can be done. You know, I know that some of that stuff is kind of sensitive because it has commercial value, and a lot of the places don't give that information away. I know that the Council for Geoscience has collaborated with them a bit, so it is possible. Yeah. Yeah.
What happened to the Feinboss during the glacial?
What happened? Okay, so the question was what happened to the Feinboss during the glacial phase? That's a great question, and the thing to remember is there's a diversity climb from west to east. So the highest diversity in the Feinboss is in the west, and then it declines as you go to the east. And the primary hypothesis for that, the reason for that, is that the west has received an enormous amount of climatic stability over the last million years or more. So the reason you would get more species when you have climatic stability is when you have instability, lineages of plants go extinct. And if you have stability, lineages don't go extinct as fast, but they still can radiate. Now, we have a stalagmite from Robertson that we're going to publish very soon, and that one dates from 500,000 to 200,000 years ago, and it is consistent with that. So it shows very, very stable climate, mostly winter rain. So the Feinboss seems to have been doing great in the west, and that would be its refuge zone when summer rains increased. And then when we move back into these warmer phases when summer rains retreat to the east, that's your zone on which you will draw the plants that then increase back onto the south coast. So I think we have a pretty good model at this point on what happened. So the west is your Feinboss biome refuge zone, but it's a strongly winter rainfall region all the time. Yeah.
How important is your work to predictions of what's going to happen with climate change in the coming years?
That's a good question. I don't think you can use what we look at to predict how climate will change, because the record we're looking at is orbitally driven. Okay, so it's natural orbital changes. But what we can do, and this is why the CSR climate modelers are interested in us, so they use their climate models to predict what the weather will be tomorrow and 5 days away, okay? Very important. But they also use the models to predict what's going to happen as greenhouse gases increase. Very important for development purposes. But how do you test the model? How do you test their predictions? Very hard. Well, they don't have an ability to test it. One way they can test it is they can run predictions based on past conditions, past carbon dioxide conditions, and then look at our records to see if their models predict it appropriately. That's why they're really engaged in this work. They can test their models against our archives. And we haven't done it yet, but hopefully that will happen pretty soon.
You've played down the archaeology quite a lot in this evening's lecture.
Yeah.
But that question that I asked is kind of, do we learn about the changes in behavior from the changes in the climate? Can that be put into the...
Yeah, for the Stone Age, I don't think so. Because the people we study were hunter-gatherers, right? We're food producers. I think if you start looking at complex societies and you see how they responded to climate change, it might be a little bit more appropriate. But so I don't think our record is relevant to that so much. We can help test models, climate prediction models, But I think that the record of humans is probably not a good analog. And you always have to keep your analogs appropriate, right? Yeah.
How can you work out how many people actually left? You mentioned 100 people. It's a
Yeah.
very small number to have such an influence on,
Yeah.
on
It's a-
mankind.
It's a good question, and the way we can do it is so most of your genome, most of your DNA doesn't code for anything. It's just baggage you've accumulated over, you know, millions of years of evolution, and then there are around, I think it's, 27,000 genes that do something right now. So a lot of that DNA isn't under selection, so it's just being copied. Now, just like, you know, if you take a piece of paper with writing on it and you photocopy it, it builds up errors. So what we can do is the vast majority of differences in DNA between us is random. It's just copying error. So if we know the rate of copy errors and we see how much you and I differ by DNA, we can estimate when we share the last common ancestor. And by the sheer amount of variation, we can estimate how many people lived at a certain period of time. So you can do those two things with it. And when you see really narrow diversity, so for example, the genetic diversity of modern humans is tiny compared to what many animals. Chimps have way more genetic diversity than modern humans. And that indicates that we went through what we call a bottleneck. There weren't many people, and there was very little variation to start with. So, you know, it's not without flaw, and it's not without imprecision. There's always plus or minus factors on the dates and the numbers, but it's a pretty good science at this point. Yeah.
Perhaps I missed you saying that. You mentioned the fact that they used heat to transform the stones to be able to work there.
Right.
But where did they get the fuel from? That must have coincided with periods when hardwood trees could grow in the climatic circumstances.
Well, it's a great question. I left that out of the talk because I knew I had about an hour. Okay, so if you plot the diversity of trees west to east, it's very low in the west and very high in the east. Trees like summer rain for the most part. Okay, all those acacias that you love to have a bride with and so on, they're summer rain trees. So the silkcrete that was heat treated becomes really abundant during the glacial, 74,000 years ago. And if you remember, that's when I said summer rains were coming in and C4 grasses. Now part of the tropical grass floral system is acacia woodland and grass. So what we think was happening was as the summer rains came in during glacial phases, acacia abundance was increasing. Now people had more fuel, wood fuel, which made it possible for them to heat treat the silkcrete. That's the working hypothesis. I mean, it's published. A lot of my colleagues don't agree with me on that. So we're having this really good debate over it. But that's why would silkcrete rise and fall? I think it's tied to the abundance of trees and wood fuel.
But some of the fynbos, like for instance the Walboom,
Yeah.
is excellent
Excellent.
firewood.
Yep.
So I mean that's sort of
I agree. And subtropical thicket, right?
Yeah.
Where you have kloofs that are protected from the fire, you get lots of trees there. I totally agree. What we're trying to do is map that and figure out, and also figure out how abundant the wood fuel is. So I have a PhD student, Chloe Atwater. She's working out of Stillby with local people, and they go out and they forage for wood, and we're measuring all of the wood and how much comes from Renosterfeld and how much comes from thicket and how much comes from Strawnfeld to try to quantify this. And so, you know, we go at it from all different directions.
Does the treated silkcrete disappear altogether, or does it just fall?
Not altogether. So it goes, like at Pinnacle Point in the glacial, it goes up to around 60–70% of the stone tools are made on silkcrete, and then during the interglacial phase, it's 2%.
So that would tie up.
So they still are doing some heat treatment. It's not the preferred technology. So, yeah.
environment, as far as the marine environment goes, with great whites and other fairly distinct species in our area, would that not also contribute to their diets?
Okay, that's a good question. We never see in the Stone Age record deep sea fishing here in South Africa. And it's a question, why don't we see that? I think it might have something to do with the lack of good lumber available to make boats. So in California, they go from intertidal shellfish to deep sea fishing. But they have cedar, tons of great wood for making. Now you have it up in the Cedarburg, but you'd have to carry it all the way down.
In the Spilbaai, they've got the fish traps.
Right, yeah.
No evidence of anything like that here?
Yes, so during the Holocene, 12,000 years ago, they're clearly really fishing a lot. So they developed really sophisticated line and tackle technology, but not the deep sea fishing. So
Fish was abundant.
Hmm? Fish was abundant, yeah. So maybe they didn't need to do that.
Need to go
Yeah.
any further.
There was enough whales washing up. And,
Yeah, there's no evidence of boats being used by our early people, which is...
No, but the question wasn't about birds, but with such an abundance, such a very rich marine environment,
Why go looking?
it must be very easily available, yet we don't seem to have any traps in that. So, did we find any evidence of them utilising fish being washed up maybe into our rock systems?
in these sites, the sites that date 50,000 and so on, they're not fishing. There's no evidence for it. But when we get around 18,000 years ago, the evidence for fishing really goes up. And by then we see really complicated fish and tackle technology.
Let's also look at it from the point of view of just how many people were alive at that stage. And because there were a lot less people, the demands were a lot less. So why go and complicate the issue and go deep sea fishing when you can just pick it out of the water?
Yeah.
Okay, thanks for your attention.